Okay.
Hello and welcome everyone. My name is Peter Robinson and this is the Ethereum Engineering Group Meetup. Today we've got Zhenyang Shi who's going to talk about Teler, a blockchain client that he has created. So Zhenyang, before you're going to introduce yourself in your slides, aren't you? Yep. All right, I'll hand it over to you.
Oh, thanks, Peter. Let me just
Yep.
Yep.
And we can see your slides.
Okay, sounds good. Yep. All right. So hello guys. I'm Zhenyang, and today I'm going to present a personal project that I have been working on for the past few months, Teler. So Teler is a trust-based, essential data, lightweight Ethereum RPC node. Before diving into that, I just do a quick intro of myself. So I'm Zhenyang, a blockchain protocol engineer at Immutable for almost 2 years. Before that, I spent 5 years at Consensus working on different Ethereum-related projects. My work has been mostly around Ethereum protocol R&D, clients, bridges, rollups, together with some other, cool Web3 projects. So feel free to check out my page where I'm planning to starting posting some of my thoughts on the whole blockchain stuff. So yeah, that's me. Let's move on to Teler. Oh, and by the way, I think I caught a cold earlier this week, so I will try not to, but I do apologize if I randomly start coughing during the presentation. So, okay, all right. So as some of you may already know, running an Ethereum node can be quite expensive. Currently, a full Ethereum node on the mainnet requires usually over a terabyte of disk space just to operate. Because of this, developers often need to rely on external node providers like Alchemy, QuickNode, Infura to query on-chain data or to perform transaction simulations. Now, for regular users, this isn't going to be an issue, but for blockchain developers like myself, having a local node can be extremely useful, especially when running a large number of simulations, tests, tracings, and just for debugging purposes, basically. So in certain use cases where a large number of transaction simulations need to be executed sequentially, having a local node can make a very significant difference because of the network latency. For example, someone could build a trading bot, just trying to determine the most optimal combination of transactions to maximize profit would benefit greatly from a local node setup due to the low latency nature. So Teler node significantly reduce disk usage by, first of all, it discards data used for block verification by only syncing from a trusted data source. As you know, Ethereum protocol is designed to be trustless, so every node needs to keep a state tree in order to verify blocks received from the network. So by syncing from a trusted source, such as syncing from, say, Alchemy, we don't need to maintain this data at all. And second, Teler only keeps chain and state data for the past hour, because for most use cases, people only care about the current state or at most the recent state. With this, Teler is still able to serve RPC calls that target chain state within the past hour. This includes ETH-call, ETH-estimate guess, and tracing APIs. Now, so you may start wonder how much disk space are we talking about here that can be saved? As of last weekend, on mainnet, Teler requires only 244 gigs to operate, while Aragon, with its default pruning turned down, requires more than 1,500 gigs. On Sepolia, 74 gigs versus 680 gigs, and on Hosky, 42 versus 262. So you do save quite some space, right? And a synced Teler node only requires no more than 10 million credit units per month with 4 credit units per second to stay in sync with Alchemy. And right now, Alchemy is offering 300 million credit units per month with 330 credit units per second throughput for its free tier subscription. So in theory, a single Alchemy free tier account would be able to support up to 30 different Teler nodes. Well, actually, that's not true. Well, actually, much more than 30 nodes, because you can sync your new Teler node from your existing Teler node. So you can basically spin up any number of nodes you want. All right. Now, you may also start wondering, how well does Teler perform? So let's take a look at the very recent early benchmark results for ETH on host key network. So to evaluate performance, I measured how efficiently different Ethereum clients handle ETH traffic, targeting recent chain state. I tested Teler against a few other popular clients like Aragon, Besu, Gas, and Nethermind. On the left graph here, you can find the performance of different clients on processing ETH that's targeting chain state for the past 20 minutes. The middle graph is for ETH that targets chain state for the past 10 minutes. And the right graph is for the past 5 minutes. The y-axis represents mega gas per second, which indicates how much gas each client can process per second. As we can see, Teler, which is the red bar in this graph, it consistently performs pretty well with performance comparable to high-performing nodes like Aragon and Nethermind. What's interesting is that as the query window becomes smaller, Teler starts to outperform Nethermind. This could suggest that Teler could actually be more efficient than other clients when processing near-head queries. Now let's just briefly go over how these benchmarks were conducted. So first of all, every ETH call is generated by randomly selecting a transaction from the past X minutes, and is simulated on the transaction's previous block state. The estimated gas, therefore, for this ETH call can be derived from the actual gas used by this particular transaction through its receipt. A total of 5 parallel actors were deployed to continuously generate and send ETH call requests to the client. And the gas consumption response time are recorded for each single request. And every benchmark runs for 5 minutes. The total requested gas and the total response time are aggregated to get the average mega gas per second. I did this benchmark on my personal laptop with 32 gigs of RAM, with every client running default settings and of their database stored on the same external SSD. You can find the benchmark tool in my GitHub repo as well. That being said, this benchmark is still a work in progress. Right now, the testing is focused on host key network and on ETH only, and only for 5 minutes, right? And because the traffic is generated real-time using real-time recent transactions, you will get different numbers if you run the benchmark at a different time. So for this particular run, every node is processing roughly like 1,000 requests per second in total. But I haven't yet benchmarked mainnet nodes or other queries like tracing APIs for direct comparison. This is something I plan to do in the very near future. So take these numbers with a grain of salt. There's still a lot more benchmarking to be done, but you can get a rough idea of how Teler's performance sits among these clients. That is why, in my opinion, Teler can serve as a very good scaling solution for Web3 providers. As Web3 adoption grows, infrastructure providers need to handle increasing traffic efficiently. So instead of deploying additional full nodes to support the growing traffic, Web3 providers can spin up lightweight Teler nodes that syncs from an existing Ethereum full node. This would potentially significantly reduce storage and infrastructure costs. As you can see in this particular diagram, even though the right side has more nodes, like 5 Teler nodes, the total storage is less. And remember the benchmark we saw earlier, each Teler node's performance is similar to a 4-node for recent state queries. So with this setup, you are getting more flexibility, better scaling, and similar performance for less cost. Okay, so far we've talked about what Teler does, how it optimizes storage. Now let's dive deeper into how it works under the hood. So Teler architecture is designed to be efficient and straightforward. So first, we've got the layered world state module. This module is responsible for storing recent world states, ensuring efficient access to account states like balances, nonce, contract storage. We have the blockchain module, which is used to store recent block data, transaction data, and receipt data. We have the processor module that wraps the EVM module, and it is responsible for applying block changes to both the layered world state and the blockchain. We have the syncing module, which fetches the latest block from a trusted source to keep Teler in sync. It uses the processor to update the world state and blockchain accordingly. It also tracks the canonical chain head and handles chain reorg when it happens. So by the way, the blockchain and the layered world state are both designed to be reorg safe. Finally, we have the RPC server, which is the main interface for external queries. The layered world states, as the name suggests, has a layered structure. As its foundation, we have the base layer, which stores the complete world state at a given block. Built on top of the base layer is a series of state layers, where each layer only stores the account state difference for its respective block. These layers are stacked sequentially, with each one referencing the previous layer. Since forks are still technically possible, a single layer may have multiple child layers. By default, Teler maintains 256 levels of layer, which corresponds to approximately 52 minutes of recent states, including all states from all the forks. So this structure makes handling reorg efficient. For example, in this diagram, reorg from layer 5 to layer 4a is pretty simple. We just need to point the canonical chain head to the new layer. But Teler, at the moment, cannot reorg beyond the base layer because the state difference has already been pruned once they fall below the base layer. Due to this constraint, Teler must maintain at least 64 layers. That is equivalent to 12.8 minutes of history, which aligns with the estimated finalization time for an Ethereum block at the moment. Well, it is important to note that this structure is still evolving. During some initial testing, I observed that having too many layers introduced performance overhead, particularly in memory lookups. As a result, I am considering an alternative approach where the base layer is positioned in the middle of the chain, allowing for both earlier layers before the base and additional layers after it. This adjustment will be explored further once a proper benchmarking framework is established. So Teler is built on top of the Gas library, particularly leveraging its EVM implementation. If you are familiar with Gas, you'll know that one of its very core components is called StateDB, which acts as an abstraction over the state tree, allowing easy access and mutation of account states. In Teler, I've defined an alternative interface called world state, which follows the StateDB interface, but is designed to be specifically for Teler's architecture. This allows the EVM module of Gas to seamlessly interact with Teler's world state without requiring major modifications. By designing it this way, Teler remains highly compatible with upstream changes in Gas, This makes it easier to integrate updates and ensure that Teler can stay aligned with any future Ethereum hard forks with minimum effort. Now I'll just do a live demo of Teler and show you how you can use it, how to sync it, and let's perhaps have Teler to answer some of our queries. Okay, so first of all, how to build Teler? Teler is written in Golang, so to build it, you would need at least 1.22. So to build Teler, it's pretty easy. Just use make build, and you should be able to find the binary here. There are a range of things you can configure at the moment. For example, you can configure the database path. You can configure the number of blocks you wish to retain, the number of states you wish to retain. There are certain configurations you can tune the RPC server, and as well as the syncing behavior. Okay, now let's try to start Teler. To start Teler, use the start subcommand. And first thing, very most importantly, is that you will need to have a block source. So this block source needs to be trusted. Normally, you can use Alchemy or other node providers, but for this demo, I have already synced a Aragon node host key network. That is why I am using a local RPC server provided by Aragon. Second, you need to provide the network this Teler node is running on. So in this case, it is host key network, and Teler only supports Druid network at the moment, mainnet, Sepolia, host key. Now I wish to have this node run to store a database under this test directory, and I will have the RPC server to run on port 9000. And let's start. As you can see, Teler starts to process blocks from the Genesis block and start building a local world state. This could take a long time. That is why for the first time, it is highly recommended to sync from a local node. And once Teler catches up with the chip, you can switch to use a node provider service such as Alchemy as the trusted block source. So for the purpose of this demo, I have also already synced a Teler node in the background as well. So let's just turn this node off. Oh, and by the way, the syncing progress is saved. So if you restart Teler node, it will picks up where it left off from last time. Okay, now let's turn it off. So this is a fully synced Teler node. It is fully synced. Therefore, approximately every 12 minutes, a new block will arrive and will be imported into this Teler node. So let's try to send some queries to this Teler node. I have already prepared a list of queries that we can use to test Teler. So first of all, let's try to get the chain ID from Teler. And let's try to compare it with the response from Aragon. And by the way, this Teler node runs RPC server on 9424, and Aragon is on 8545. And we get the same result. This is the hex representation for the chain ID on host key. We can also get the block number, the latest block number, and the latest block body. Then just to test, we can read the block data. Then let's try to read the world state. So this query is used to read the ETH balance of this first account. which has a lot of ETH balance already in it. And the second query is to get the ETH balance for an empty account. Hopefully we get 0 back because it's empty. It does not have any ETH stored in it. Now let's try to do a gas estimation. The first request, we try to estimate gas for a simple ETH transfer from the first account to another account. And we get a result back. So this is the gas required for a simple ETH transfer. So it should be 21,000. The second estimation gas request is for the from the empty account, and we are getting an error message back. That is because this empty account does not have any ETH balance stored in it. And we will also see a corresponding warning logs pops up inside Teler. This is the same for the ETH call as well. The first ETH call is for a ETH balance transfer from the first account, and it returns 0, which indicates this ETH transfer is going to be successful. And the second ETH call is for a simple ETH transfer from the empty account, and it failed with the same error. But what's special about ETH call is that you can actually do state override inside a ETH call request. For example, this request is still doing a simple ETH transfer from the empty account. The difference is that we are using state override to forcibly setting the balance of the empty account to be 1. If we do this, we are getting a success result back, right? It only works for one-way transfer. If we want to transfer two-way, then it failed because we only setting the balance to be one-way, basically. Next, as I mentioned, Teler only stores recent states. So what happens if you try to do an ETH call on a relatively older state? So this block number is a block number from yesterday, and we are getting an error back. Data store key not found error, right? So this is because the state associated with particular block has already been pruned. It's from yesterday, right? I should probably have a more appropriate error message for this type of errors. So this is something, of course, I will fix very soon. And the Teler also supports expensive queries as well. For example, we can try to trace the latest block. And Teler will respond all the traces during the latest block execution, basically. Yeah, and we get the traces. So this is for the more expensive RPC queries. So, and finally, let's try to do some load testing. Let's try to throw a relatively big traffic to this Teler node. I will be using this benchmark tool that I just mentioned in the slide. So what we can do here is let's try to throw a large traffic to the Teler node, and let's try to do the same for the Aragon node. As you can see, there are a lot of error messages, well, warning message pops up in both nodes. That is because when the agent sampled a reverted transaction and you try to replace that reverted transaction, you get a warning log. And because we are sending a lot of requests to these two nodes, you get a lot of warning logs, basically. At the moment, we can see that looks like Teler is performing pretty similarly as the Aragon node, maybe slightly better, but at the moment, both nodes are processing roughly like 450 requests per second at the moment. And let's have a look at the resource required. So Aragon at the moment is taking 10 gigabytes of memory, but Aragon is only taking 5 gigabytes of memory right now at the moment. This is only the case for hosting network. All right, the story will be different on mainnet. So on mainnet, Teler is actually consuming more memory than Aragon, something I will talk about very, very shortly after. I will pause here for a moment. Is there any questions if I move on?
Not a question, but yeah, this is awesome. I mean, and I think being able to do the really heavy tasks like tracing in a node like this would be good because, you know, that will be really, really helpful.
Yeah, that's the case. Yes, tracing is very expensive through node providers. So having a telenode, well, just like having a cache layer inside your local machine where you can perform a large amount of heavy computational heavy request to your local node, basically. You save a lot of cost. All right, we'll turn off the load test. And let's continue to the next slide. All right, now that we've explored how Teler works today, let's take a moment to talk about where it's heading next. There are several major areas of improvement I'm actively working on, and some more ambitious ideas I would love to explore in the future. So first of all, having a robust benchmarking framework is crucial. To continuously improve Teler, we need a structured way to evaluate its performance, identify bottlenecks, and explore areas for optimization. Then, I would also like to experiment different database options. Right now, Teler uses BadgerDB as the only database option. However, I'd like to explore alternative databases to see if we can further optimize the performance. One current issue is memory usage. It's not an issue on hosting network, but on mainnet, Aragon only requires around 13 gigs of memory, whereas Teler needs 17, most of which is consumed by BadgerDB. So by fine-tuning Badger's configuration or by experimenting with different storage solutions, we could potentially reduce memory overhead and improve overall efficiency. And next, support other chains. At the moment, Teler is built only for Ethereum, but supporting additional EVM compatible chains like Polygon, Arbitrum, Optimism, and of course, immutable zkVM would allow developers to leverage Teler across multiple ecosystems, improve its usability. And next, support SnapSync. As you probably already noticed, a major challenge with Teler today is that it requires a forcing, that is processing every block from Genesis to reach the latest state. This is slow and inefficient. To solve this, I plan to implement a feature that will be similar to SnapSync, allowing Teler to download latest world state directly instead of replaying historical blocks. This will enable new nodes to sync much faster, significantly improving onboarding time. Another interesting idea is partial state storage. We can allow users to store only the state they care about, for example, just certain contracts, or as you know, on Ethereum, there are quite a lot of inactive accounts at the moment. We can also store in only active accounts while pruning inactive states. This brings us to the last and perhaps most interesting idea. So today, RPC providers, Alchemy, Infura, QuickNode, they are all centralized services. But what if we can create a peer-to-peer protocol to act as a marketplace for computation? Imagine a network where users could run a telenode and start selling their computation power to developers, creating a decentralized alternative to Alchemy. So instead of like relying on a few large infrastructure providers, applications could query a distributed network of nodes, reducing reliance on a centralized RPC providers. So yeah, these together with a bunch of other things. And finally, Teler is an open source project. If any of these areas interest you, whether you want to contribute to the development, you want to test Teler, you want to explore how it could fit into your own infrastructure, feel free to reach out, and I would be more than happy to connect. Thank you. Now I'm happy to answer any final questions that you may have before handing over back to Peter.
Have have you been in have any RPC provider companies got in contact? Because I would have thought for them this would be awesome, because as you showed in your diagram, they could just have far fewer RPC provider nodes and lots of Teler nodes to massively save on cost.
No, not yet. This is actually the first time I'm demonstrating this piece of software for the first time in public. I am planning to do a proper announcement sometime later this week, because previously there are still some like issues here and there. So I was busy fixing those issues. And now it's reaching a more mature state, and I'm like kind of like ready to announce it.
Okay, great.
Cool.
And is there any other questions from the audience? Okay, I think you've explained it very well.
Cool. Thanks,
so
Peter.
people who might be watching this on YouTube, if you're interested or got questions, put them in the comments, and Zhenyang will see them there. So that'll be another way of asking questions.
Yep. Okay, I'll handing over back to Peter. All right,
Yes.
for the next slide.
Yeah, please go ahead.
I have one question. Can I ask?
Yes. Yes.
Yeah. So there are some other node implementations like Reth, right? Reth SDK. They are creating like an SDK where we can use different components, right? So have you explored reusing those components? Like, for example, you mentioned here SnapSync and all those things. So they have implemented and they made it modular. So I'm just wondering, have you explored such reusable components?
You mean the REST component, right? The REST one?
Yeah, Reth SDK, Reth node.
Yeah. I'm actually, no, I haven't yet explored yet, but I am planning to look into the REST modules for sure, because from my understanding, REST seems to be performing also very well. So yes, totally, I will be exploring.
Okay. Thank you very much. It's very interesting.
Thank you.
To explore. Yeah, thank you.
Cool.
Yes. The merch store. Merch store is still open. Yep. So there's the merch store. Go there, get a t-shirt. Next slide, please. So next week, or actually in 2 weeks' time, Dr. Ermias Abibi is going to talk about data availability and just what's out there and how does it work? What does it mean? How would you use it? We've got Arajana, who's going to talk about essentially analyzing blockchain transactions and seeing anomalies, seeing things that might be malicious. And I'm in discussions with a few different people about future talks. So I think in the near future, we're going to have a range of talks coming up, which will hopefully be interesting. And next slide, please. Okay, if you're here today, you can watch the recording of this and other talks on YouTube. If you are watching this on YouTube, you can click on that link and join the meetup and ask the tricky questions live. There's a Slack invitation link if you want to join the Slack workspace to have discussions. There is example code to some talks, and that can be found at that repo. So look, if people are interested in doing a talk, either on Ethereum, core Ethereum, cryptography, on applications, DeFi, or whatever project you're working on that you're passionate about, please get in contact, either LinkedIn, Telegram, Twitter, and let's discuss, and maybe we can schedule a talk for you. All right. So thank you again, Zhenyang. That was a really good talk, and I'm looking forward to watching as Teler takes over the world.
Thanks, Peter. Thanks for having me.
All right. Thank you, everyone. See you next time. Bye-bye.
Bye. Bye.